Hello and welcome to Vintage Computer Festival Pacific Northwest 2018, our first one. Right now we're going to turn the stage over to Peter Glaskowsky. Peter is going to talk to us about the first 50 years of the microprocessor, not just history, but also insights on what we're going to be doing for the next 30, 50 years, 20 days maybe. We'll see what we can do. Show us the crystal ball.
Or until the hour is over and Mike kicks me off the stage. I don't know how many people here are actually microprocessor experts. Can you raise your hand if you consider yourself to be in that category? Okay, not too many, great. So for most of you, I hope there's a few things here I can teach you. And if you are a microprocessor expert, I am sure there are things I can teach you. I am currently a consulting engineer, mostly in intellectual property consulting. I live here in the Seattle area. I used to be editor-in-chief of Microprocessor Report, and I think that's probably where I'm best known from. But after that, I worked as a vice president of system architecture at an x86 startup company called Montalvo Systems, which probably very few of you ever heard of. We burned through about $85 million in 4 years, and then got kicked in the butt by the 2008 recession, and we almost all got to go home. I've also spent a couple of years at Intel and a couple of years at Microsoft most recently, which is why I'm up here. If you like this talk, I'll be giving more talks at Norwestcon, the science fiction convention, at the end of the month, end of next month. In 2006, I gave a presentation on basically 30 years of PC system evolution at a vintage computer festival in Silicon Valley. That was when Moore's Law was healthy, and so I had a lot of big numbers to talk to people about, right? Not just 1,000,000 to 1 in some cases, but there were some improvements over that period of time that were well in excess of Moore's Law. That was mostly a system level perspective. Here I'm going to be focused more exclusively on microprocessors. In the last 12 years, more or less, we have seen some elements of the PC platform not evolve very quickly at all, right? You could get, well, that's not a MacBook, but it looks like one, but I have a real MacBook that had gigabit Ethernet in them, and you still get MacBooks with gigabit Ethernet in them. Yay, progress, right? But on the other hand, your home internet connection has probably become 30, 40, 50 times faster than it was then, unless you have DSL, in which case you're probably very close to the same speed. We've gone from fairly slow hard disks to really, really fast SSDs. That's probably the most noticeable improvement we've seen in the PC platform on performance. Disk capacity has also gone up a lot. Basically in 2006, you could buy at the very high end of the market a 750 gigabyte hard disk, and now you can get 12s, which is not bad. Not Moore's Law speed, but then hard disk capacity has never grown as fast as Moore's Law. But let's talk more about the microprocessor. CPU core performance improvements over time have simply been disappointing. Well, in the 10 years from 2006 to 2016, the fastest CPUs published benchmarks through the spec organization that increased by about 4.2 times. And that's 15% a year. And that's way, way short of Moore's Law. In the same time frame, we might have expected to see 100 to 1 improvements in the days of Moore's Law delivering everything it could. And we simply have not, because they have put the effort into other areas, right, going to multi-core and so on, and we'll be talking about that in much more detail. But I would like to walk you through some of the history of the microprocessor in the hopes of explaining why I am now claiming that we are at 50 years of the microprocessor, which would take us back to 1968, when everybody knows that the first microprocessor came out in 1971, because, well, we'll get to that. Microprocessors, of course, evolved from mainframes and mini computers. They started out with, well, actually relays, the Conrad Zeus machines, through tubes and transistors and integrated circuits over the preceding few decades. And basically the integration served to shrink the machine. And eventually we got to the point where we could put an entire reasonable 8-bit computer on a single chip or on a small number of chips. And in that time frame, the complexity of a microprocessor was, you know, thousands to maybe 10,000 transistors. That was enough to give you a decent 8-bit machine. And this is an IBM mainframe from 1968, the same time frame that we're talking about here for the origins of the microprocessor. I'm getting out a laser pointer. Actually, a laser pointer I have to unlock. Things you don't think about in advance. But you can see that this is, even for 1968 in a mainframe, this is a fairly simple, straightforward CPU. There's an instruction unit where they have an addressing adder for things like offsets, and then in this machine at least a single integer execution unit, which has basically a 64-bit adder, and then a separate adder for other purposes. This machine could do floating point, but it did this mostly through software. They had machines with native floating point available, but the Model 85, which happens to come from the 68 timeframe, doesn't have that. But you will see that these have very wide interfaces, right? 16 bytes, 128-bit wide, access to main memory, and so on. And that's really where it derived its performance from, and of course clock speeds and so on. The first microprocessor was definitely not the 4004, but you can certainly say that was among the first. The Garrett MP94 began to be designed in 1968. They had a very clear plan for what they were trying to do. This is for a US Navy contract for the F-14 aircraft, part of the, basically the flight control system. And you'll notice the sub-bullet that points out that this project was classified. And so when we think about this poster, which came from Microprocessor Report, Microdesign Resources, the company where I was working in '96, this is represented as the first 25 years of the microprocessor, but it starts in '71 and conspicuously does not include this chip because that chip was a national security secret. And so we couldn't very well put it on here. I still haven't praised him on it, but Nick Tredenick, who was one of our board members at the time, was in US Naval Research, and he was a naval officer. And I believe he probably knew about this chip, he just couldn't tell us. Can you imagine the tension that must have been in his mind? Oh, I know something you don't, but it's illegal for me to tell you. Nick was a pretty cool guy, though. Or it still is a pretty cool guy as far as I know. And, you know, there were other projects going on at the time that would have resulted in single chip microprocessors and other multi-chip designs. But we really didn't start to get much progress on those until a little later. There was a fellow named Gilbert Highet who was famous in the 90s for having filed a patent on a single chip microprocessor basically in the early 1970s. It spent 20 years going through the patent system and then suddenly emerged to great fanfare in '91, if I recall. And his company held up a bunch of other companies and said, so it turns out that these single chip microprocessors you've been building for all of these years, all your base belong to us, right? We own the patent on the single chip microprocessor, so you have to start paying us vast amounts of money. His patent was actually eventually squashed, and so nobody had to keep paying him money, but he did make a good bit of money for a while there. Probably the first microprocessor-like thing that appeared in a commercial product was the 4-phase AL1. This was a chip set that was intended basically for a programmable terminal. Back in those days, as an aside, if you were trying to sell a computer and it would fit in a small space, you couldn't call it a computer because nobody would believe you. And so mostly they sold these machines as terminals that could be locally programmed. but they wouldn't use the word computer. It connected to a computer, and it could be locally programmed, but it's not a computer, and that was how they helped people figure this stuff out. Hewlett-Packard had a machine called the 9830, which was a basic programmable machine with an LED alphanumeric display on the front, and they called that a calculator, but it was programmed in BASIC, and it could run any program you could write in BASIC. It had some weird omissions I've run into looking through the documentation, like there was no way to put a double quote in a string. Okay, it simplified the coding, I'm sure. But that was actually based on a simplified version of their 2100 series mini computer. It did not have a microprocessor. Now, that came out in '71, by the way. Complete personal computer. They just didn't call it a computer, and so most people overlook it. The AL1, again, as I said, was a chipset. Some people say, well, you know, if it's a chipset, then it doesn't qualify as a microprocessor. I am here to tell you that even the 4004 did not really qualify on a commercial basis, at least, as a single chip microprocessor, because although when you look at the block diagram of the 4000 chipset, it looks like there's a single chip CPU and then everything else is memory. In fact, the 4002 RAM, which was essential to the operation of the machine, was actually designed around some logic on the chip to participate in instruction decoding. And if you couldn't run the machine without a 4002 or something like it, if you couldn't use that as a CPU, then I think you have to say the 4004 alone was not a single chip microprocessor. That's an opinion, and there doesn't seem to be anybody from the 4004 design team here to throw rotten vegetables at me, but that's my opinion anyway. The Pico 1 and the 4004, incidentally, were both designed for calculators. You're probably aware of that. There's probably some floating around here somewhere. But they were feature complete from a microprocessor standpoint. They did everything that we would today expect a 4-bit or an 8-bit CPU to be able to do. There were, at the same time, in the late 60s and early 70s, a number of other single-chip calculator CPUs that were not feature complete. They did not have, for example, a lot of support for the conditional branching functions that we're used to, or general purpose I/O. Many of them were designed just to connect directly to an LED array or something, and did not have other input-output options. And so, for most purposes, they didn't count as microprocessors because you couldn't reapply them in some other way. So, over the time since then, of course, we've seen tremendous evolution in microprocessors. And it's useful to understand what drove that evolution. And obviously, these were companies trying to make money. And the way they made money was by delivering more performance. And that's performance from the end user perspective. How fast did their application run? And there are many different ways of delivering performance. I don't mention it on the slide, but you can add hardware-specific functionality to a chip that makes certain kinds of operations run much faster. And that isn't, strictly speaking, the clock speed or the number of instructions per clock, but it delivers additional performance. There were two ways of getting clock rates to go up. One of them was just waiting for process technology to do that for you. And everybody got that advantage because everybody had access to good process technology. And over time, early in those days, it was 3 or 4 years or so between processes up until more or less the late 1970s. But if you waited for the next process, your old design would magically run faster on the new process, and that was one way to deliver more value. But the more profitable way was to hire smart people to figure out ways to optimize the circuits so that they would run faster on a given process technology. And we'll talk about a lot of those features. Pipelining, for example, is a method of letting instructions start more quickly, more often in time. And then orthogonally to that, you could increase the number of instructions per clock by logical enhancements, like running instructions in parallel or running just parts of instructions in parallel. And then much more recently, speculation, which is basically a feature by which you try to predict which instructions of the ones coming up will be the ones you will actually need to execute. And then you run those, and then you later figure out whether you should have run them or not. And if you weren't supposed to run them because your program actually took a conditional branch in some other direction, for example, you throw away that work. And we'll talk about some of the hazards of that, which have been much in the news lately, as we get later in the presentation. So clock speeds in those days, say around 1970, were really severely limited by the very simple processes they had. They were logically sufficient. You could make chips that would be feature complete and would run, but they were pretty slow. That MP94 was a 375 kilohertz clock speed, and in fact, it was bit serial. It did only 1 bit of calculation for each one of those clock periods. And as a 20-bit machine now, if you do all of the math, it had to do an instruction phase and then a data processing phase. They were only able to run 9,370 instructions per second on that CPU. So you can compare that against more modern 16-bit CPU running at multiple megahertz, and you can see that that whole transition happened over a period of about 10 years. The spike in performance that came into the microprocessor market was really quite dramatic. The 4004, just a few years later, basically another generation of process technology, could run at 741 kilohertz, but there, a single instruction was divided into 8 phases, like pulling in the instruction and then decoding the instruction and then performing one part of the operation, performing another part of the operation, writing the data back to registers. We'll talk about more of the pipelining stuff. But it had to do all 8 phases of those for one instruction before it could move on to the next one. And so although it was running at what seems like a high clock speed, it wasn't doing an 8-bit operation, 741,000 times a second. In fact, it was doing only 92,583. That's a precise number. I'm not sure how accurate it was. 8-bit operations per second. Now, you move forward to 2012, which happened to be really sort of the golden era of PC overclocking because of the way people were designing chips. There were people who would immerse AMD processors in liquid nitrogen to keep them super cold because that allows the signals to move faster on the wires in the chip. And a couple of people that I was able to find records for on the internet got these chips running at 8.8 gigahertz. So that's kind of your point of comparison, right? From 375 kilohertz up to 8.8 gigahertz in this time frame. I will say also that in 2012, IBM introduced a Z Series processor for basically the descendants of the IBM 360, right? There are still IBM machines you can buy today that can execute decks of code, and I mean like decks of punch cards. That's where the word deck comes from the IBM 360, because those CPUs have evolved incrementally over time. They're dramatically more complicated now. They're really wonderful designs, but they're still capable of running really, really old software, sometimes a little bit of tweaking, but that's usually not much. But anyway, they've delivered chips in that family at 5.5 gigahertz, which is pretty good for a server, especially that's sold into things like the banking markets, where they do not want any measurable level of unreliability. So to deliver a commercial chip into that market at 5.5 gigahertz is, to me, a more impressive accomplishment than delivering a liquid nitrogen cooled and generally fairly flaky consumer processor. So a little bit about pipelining. I'm not going to go into this because I know that there will not be a test at the end. And in any event, probably none of you are still pursuing degrees because I can see how much silver hair there is out there, or sometimes not so much hair. You don't need to know this for professional reasons, but it's still kind of useful to know from the perspective of the presentation. So this is an example of a design where each instruction is divided into 5 phases. Each line on the diagram represents a different instruction, and each horizontal division represents a different clock cycle. And what this means is that even though the instruction takes 5 clock cycles to complete, you were able to start a different instruction every clock cycle. And so your throughput here, ideally, is 1 instruction per clock. There have been examples of CPU pipelines that were insanely long. There's a famous Intel project called Tejas, which was supposed to be a 40-stage pipeline x86 chip. This was part of the Pentium NetBurst, right? The Pentium 4 series, right? This would have been the last Pentium 4. Well, at least it became the last Pentium 4 to be designed, because at some point they started taking these designs around to their customers, letting them try out the machines, early prototype chips and so on, and discovered that they were really not very good. They had huge, huge power consumption because of all the extra logic required to implement these crazy deep pipelines. And so if you had a budget for your data center or something like that, these machines would give you less performance than the previous generation that had a 30-stage pipeline. And this was what led to the end of NetBurst, the Pentium 4, and why they got pushed to the next generation. Today, we've settled out with on the order of 14, on the close order of 14 stages. Longer for complicated instructions, shorter for simpler instructions. Superscalar is where you're able to start 2 instructions on the same clock edge. There is a requirement here that the 2 instructions be independent. That is, that you can't have the second one be waiting on the output from the first one, because it won't be available. And in fact, this dependency issue pervades the entire field of CPU design. Dependency management is really one of the key central skills or secrets of the CPU industry. And it fits into so many different ways, fits into that industry so many different ways that it's even, I think, outside the scope of the talk, but it's a very important point. So how does this all go together, right? Well, this is a diagram of the Intel 4004. This is a Wikipedia redrawing of the block diagram that's actually on the front page of the Intel 4004 data sheet. But this one is actually much easier to read. And so the way that instructions operate here is that you can see there's basically one internal data bus. And so every time they need to move data around within the chip, they have to separate that movement from some other data movement that's going to be also part of the same instruction. And so what you would see is they'd move data from a register into an accumulator or a temp register, and then they could feed these 2 things into a single integer or 4-bit ALU. And then its results would go right back out to the data bus, and they'd have to figure out where to put that when it was done. It could either go back into the accumulator, it could go into a register, or whatever. And so, as you can see, there was a lot to do. They needed 8 stages in each instruction to be able to get all of this work done. But each instruction had to wait until the previous one was complete before it could move on. Now, if we take a great leap forward, 2014, IBM's Power 8 gives us an example of a super pipeline, Superscalar, sort of everything is there kind of CPU. Here, instead of a single integer ALU, there's a pair of them. Instead of being 4 bits wide, it's 64 bits wide. And it is joined by a ton of other ALUs. You can see up here that there's room to decode up to 8 instructions at a time, even though you will see considerably more than 8 blocks here. And that's because they understood that they'd never be able to keep all of them busy anyway, and there was no point in providing parallel decoding for a larger number of instructions. But under ideal conditions, a programmer, or a compiler mostly, would be able to figure out ways to keep up to 8 of these things operating on each clock cycle of each instruction. And so the theoretical throughput of this chip, is literally orders of magnitude higher than the theoretical throughput of that Intel 4004 at the same clock speed. Now, in practice, there's not a lot of code in the world that's really good for keeping high utilization of any particular mix of ALUs. This is what we call an application sensitivity. That is, a given CPU design will run better on some kinds of code than others. And the range of difference, especially on these more sophisticated designs, can be huge. That itself can be an order of magnitude or 2, depending on various design optimizations. So what are all of those features? Well, I've talked about a couple, right? The superscalar and pipelining. There's also something called out-of-order execution. where the CPU can simultaneously look at the next n instructions that are prepared to be executed, and it can look down that list and try to find instructions which don't depend on any of the ones that are still waiting, and run those out of order. It can say, well, I see that later on you do a memory load into a register that I won't be using until then. So I can, what we call, hoist that load earlier in the flow of the program, right? Maybe your compiler, didn't know how to do the analysis to figure out how early it could initiate the load. But since memory loads can take a long period of time, many clocks in the CPU because the memory is far away, it's beneficial to be able to start memory loads as soon as possible. Out-of-order execution is a really big deal with benefits that are, again, very application sensitive. Sometimes it helps a lot and sometimes it doesn't help much. Just to note, that is both the acronym for out of order and the emoticon for a startled pig. I deliberately allow this to tail off. It's just intended to show you that there's a lot of these features. In fact, that list could be far longer. I just didn't want to take the time to prepare it. When do these features show up in microprocessors? Well, of course, in the 1970s, as I said, we saw very rapid progress. We went from 4-bit to 16-bit registers and data paths and so on. A lot of specialty chips started incorporating features that we see later on. By the 1980s, people were routinely pumping out 32-bit chips, and they were pipelined, and they were superscalar, and they added virtual memory. A lot of the early virtual memory implementations were actually a separate chip to the main CPU. And that's another example of why a multi-chip design, to me, still qualifies as a microprocessor. It's an essential feature for the customers, but it's on 2 different chips, and that's still fine. To me, that's still a microprocessor. In the 1990s, we achieved 64-bit processing with the MIPS R10000 and various other chips. We got to super pipelining, which is a very deep pipeline. We got to SIMD, which is single instruction, multiple data. It's also known as vector processing. So if you're familiar with almost any of the modern CPUs from Intel or AMD or the other major companies, they have vector extensions that let you do the same operation on multiple items of data in parallel. And so even though you might have a 64-bit CPU, it might be able to do 128 bits or 256 bits or 512 bits of parallel operations on shorter data items. Typically, you will see these implemented for things like 8-bit, 16-bit, 32-bit quantities. By the 2000s, we got to the point where you could put a fully feature-complete 32-bit design on a single chip. And in fact, we got to the point where roughly by the mid-decade time, you could put 2 of these on a chip. And that's when that started to appear, right? So you had chips like the Core 2 Duo from Intel, had 2. You could write applications so that they had multiple streams of execution that could be run in parallel because they had no dependencies between the 2 streams. And so this was a low-hanging fruit kind of thing, right? So we went to dual-core 32-bit before consumer PCs mostly went to single-core 64-bit because the dual-core solution was a better fit to the application workloads that most people were using. Once we got to 4, and again this happened also in that same decade, that's when the attention returned to moving up into wider bit widths because 4 is starting to get into the area of diminishing returns in CPU design. If you have much more than 4 cores, it may not help so much, and I'll talk about that later as well. So a little bit more about bitness, because this tends to confuse people that are not in the industry, and it's important to understand the differences. There are 2 categories of bit width that matter in a CPU. One is how wide is your data, and the data paths and the data buses that are used to convey that data from one part of the machine to another. And the other part is how wide are your addresses. Now, there are inconsistencies in both categories, and don't worry too much about that, but in the general sense, that's your breakdown. When we were looking at those early microprocessors, they typically had 8-bit data paths and 16-bit addressing, but we called them 8-bit processors because what was more important in that time frame was the data width. There were 64-bit chips, like that R10000, that had 33-bit addressing, because basically there was only so much memory you could buy and afford to put on the CPU, and if they had made it way more than this, right? So that's 8 gigabytes of RAM. You can imagine the mid-1990s, a machine with more than 8 gigabytes of RAM would have been a exceptionally well-equipped machine, and probably too expensive for most customers to afford. And so they provided as many address bits as they sort of thought was useful or necessary. As an aside, I've always been annoyed by Intel because they use address width as a very arbitrary function in a lot of their chips to divide the expensive versions of the same silicon chip from the less expensive versions. And this ends up generally giving us things like laptops where you can really only install maybe 100 or 200 bucks worth of RAM, even if it would really, really help you to be able to go to 2 or 4 times that much RAM, right? You get a good expensive laptop, it might be 2,000 to 3,000 bucks, but you can still only put like a couple $100 worth of RAM into the thing. Even though it would be great for you, it would make the laptop significantly more valuable if you could put 400 bucks worth of RAM into it. That's mostly an Intel-driven thing in this industry. I will note that no CPU, as far as I can tell at this point, supports 64-bit physical addressing. And I did the calculations. If you had the really tall server racks, the 48U or 52U server racks, you would need about 100,000 of those racks to put in 2 to the 64th bytes of RAM. And nobody wants to build computers that big, and that's why nobody makes CPUs that have 64 bits of physical addressing. We're just not there yet. Probably we still won't be there yet by the time Moore's Law runs out, which I will also address a little bit later. So when you hear about bitness, mostly we're talking about the data path width. Sometimes you will see somebody talking about a 64-bit CPU because it can address more than 2 to the 32 bytes of RAM, but mostly that isn't the way that the word is used. I mentioned multicore earlier. In the 2006 presentation I gave at VCF, I wrote, dual-core chips are just the beginning. CPU vendors will keep increasing the number of cores on a chip until it stops helping. In fact, they kept increasing the number of cores on a chip until well after it stopped helping. Mostly because people will buy more cores just for bragging rights. We have this relatively new AMD Threadripper chip, 16 cores. The number of workloads out there that real people run on these machines that benefit from having 16 cores instead of 8, it's a very short list. Some of them are very real applications, don't get me wrong. I mean, there are people that legitimately buy and use these machines for things like video transcoding, where it's a big win, right? You would definitely want to have this chip for some of those workloads. But for gamers, right, the version of that chip that has only 8 cores running is actually faster, because the power consumption that would be used just to keep the other 8 cores alive would actually require you to slow down the other 8 cores that you are using, because there's basically always temperature limits on CPUs. And so, you can see people on the forums on the internet talking about the fact that they bought an awesome 16-core Threadripper to play games. And if you're lucky, you see somebody else on the forum trying to gently explain why that was a mistake. More commonly on the forum, somebody will just be highly critical, I guess. It's probably the safest way to say that. So this is a slide that I found, which I find, oh, I'm sorry, that's the next slide. I'm using the presenter mode, and sometimes I get distracted by something coming up. But the bottom line on these new features is that they don't really help you as much as the previous set of improvements did like 10 years ago, right? We saw much more rapid performance improvements over time than in say, the 80s and into the 90s than we have seen since. Because a lot of these features don't deliver the kinds of improvements that used to be associated with the same number of transistors that had to be added to the chip to get to them. Sure, modern CPUs support 64-bit math. How often are you manipulating 64-bit variables? right? 64-bit integers are very rare. There's plenty of languages you can get that don't even support them, right? And if you're running something compiled in a language that doesn't support 64-bit variables on a 64-bit chip, maybe the only place you get to use that is when they've got specialized data movement instructions to move a big block of memory from one place to another. And so they can, pull in 64 bits from one source and put it back out on the bus going to somewhere else. And sure, that's an improvement. But there were easier ways to achieve that than to design the whole CPU to support 64-bit operations. In Superscalar, right, I showed you a chip that can do 8-wide Superscalar. The fact is, when you run most applications, you may be completing fewer than 2 and sometimes fewer than 1 instruction per clock on average, because it takes so long to get new pieces of data from memory. And so if you have highly unpredictable patterns of memory addresses that you're trying to load into the CPU, every time you issue a new memory load, it gets stalled and it has to go out to the cache, or the level 2 cache, or the level 3 cache, or the level 4 cache, or all the way out to DRAM. And that can be hundreds of CPU clock cycles of waiting for that thread. Now, a smart CPU will find some other thread that's waiting to run, and it will, try to find something else to do with the hardware that's available to try to keep progress moving forward on the machine. But nevertheless, the average throughput tends to be pretty low. And one of the secrets of this industry, secrets to the outside, well-known inside, is that many, many years ago, IBM wrote a great paper where they simulated multiple issue designs, highly superscalar designs, and basically told everybody, as far as we can tell, 6 is about as far as you'll ever really want to go. But who had that 8-way design that I was showing a minute ago? It was an IBM chip. So even though they knew perfectly well that there were very vanishingly few applications where 8 was better than 6, they still designed an 8 for competitive reasons. Right? That continues to happen. Simultaneous multi-threading, you may have heard of this, right? It's called hyper-threading and other things in the real-world market. Speculative execution, which I talked about, generally multi-core beyond 4 or some number like that. Those are not always beneficial, and they can be actively harmful. One of the broad generalizations we can make is that very performance-intensive applications like having these features, but how many performance-intensive applications do most of us run? Right, well, I mean, this is PowerPoint, doing a PowerPoint slideshow. How heavily loaded is this CPU right now, right? It's probably giving the equivalent of about 40 megahertz of sustained performance right now. And yet, I'm sure this must be a, probably 4-core chip that's 2-something gigahertz operation. Well, that's mostly being wasted right now. And in fact, there are entire categories of machines, which we call smartphones and tablets, where you generally don't ever run applications that are extremely performance intensive. And so basically, that gap, the fact that Intel and AMD and other companies focused on the really high performance applications and stopped paying so much attention to the fact that there are a lot of applications that don't need high performance, that's really what opened up the opportunity for companies like ARM to come in and to work with, maybe more clearly thinking companies like Apple, for example, to create another class of machine that uses only relatively low performance CPUs to run only relatively low performance applications. I was part of a team interviewing John Sculley, the former CEO of Apple, for the Computer History Museum many years ago. I'm very pleased to say I was not actually the guy who wrote the questions to ask him, but one of the questions that he was asked was, how do you feel about Apple having lost so much money on the development of the Apple Newton? Right, because it was well known that Apple had spent hundreds of millions of dollars on developing the Newton, right? It was a big, expensive project, and they sold, 80,000 units and lost a vast amount of money. And Sculley got quite angry at the fellow who was asking the questions. I was the camera operator, so I'm innocent here. And he said, do you have any idea how much money we made from the Apple Newton project? And the Q&A guy was like, you made money? He goes, we made $700 million on the Apple Newton. And we're like, I mean, I too was like, how could this be true given how much money you were known to have spent and how few units you sold? It was the fact that they had anticipated the need for low performance, high efficiency microprocessors that caused them to invest money in ARM. And it was the ownership of ARM. Apple was one of the major shareholders in the ARM company in the early days and held it for many years, that made them this vast amount of money. Yes, they lost money developing the actual product, but they recognized the opportunity for the product, and even though they didn't get the product right, they did the right thing to make the product possible, which was investing in ARM and making a lot of money when ARM went public and Apple sold off its share of the company. And to me, that was a very powerful lesson that has stuck with me. Here's the thing I was distracted by. It's a nice diagram I found online that basically shows us that the growth in transistors has been a straightforward exponential. And when I say that, I mean that this is a linear time scale and this is a logarithmic time scale, right? So this is what we call a Semilog diagram. Straight lines on a Semilog diagram actually correspond to big exponential growth. So even though this seems to be a straight line, if this were a linear scale of thousands of transistors, this would look, like this, right? It would end up with something that would look very much like a vertical line. It would quickly grow so fast that it is beyond the scale of the drawing to be able to show us. Because, this spans a range of literally, 10 million to 1. So we see the transistor count keeps going up. And this is still true, right? Each new semiconductor process really does basically double the number of chips we get. The processes may not be coming at 18 to 24-month intervals anymore, but every time there's a new process, every 3 years, going maybe to 4 years, we do roughly double the number of transistors. The question is, what do we do with them, and what can we do with them? So we see that single-thread performance has this definite inflection point, and this is quite a dramatic thing on a semi-log scale. What this means is that the exponential that was holding true during this period of time drastically fell off. And single-thread performance has only been growing relatively incrementally, right? You can see that this takes us basically from that 2006 to 2015 timeframe, and it's only gone from, that's probably like 2 times 10 to the 4th up to like 8 or 9 times 10 to the 4th over like 10 years, right? That's that 4.2x improvement that I mentioned earlier, displayed graphically. It's not very impressive. Clock frequency has actually almost leveled off. The diagram actually kind of hides that. Clock frequency continues to improve slowly, several percent a year, 5%, maybe 10% in a good year, but not the way it used to. And so you've noticed, right, Intel is now up into the 4 gigahertz territory with x86 chips. You go back 10 years and they were, if you have an apples to apples comparison, not Pentium 4, but like the old Core and Core 2 families, right, they've gotten faster. They've gone from a couple of gigahertz up into the 4 gigahertz territory. But that's a relatively slow rate of improvement. Power has leveled off, but not for the reasons you'd think. Some people are still happy to make chips that consume very large amounts of power. Not ironically, the Power series of microprocessors from IBM, like the one I showed you earlier, they come on modules that can consume kilowatts of power. 4 chips, 4 cache chips, 2.5 kilowatts. They do not use regular heat sinks and fans like you're used to in your PC, right? Those machines are commercial liquid-cooled machines because it's the only way to get that much energy out of a package. PCs can't afford to use that kind of technology in high-volume systems, and so they are basically limited by how good a heatsink can be, and they stick into that range for most PC purposes of say 90 watts to 120 watts, thereabouts, sometimes a little bit higher. Laptops, have basically come down in power consumption since the days when they were like 2 inches thick to the current days when they're like, 3/4 of an inch thick, because they find it's easier to sell the machine when it's thin and light. And what's happened basically is that all of the transistors that we're getting have been turned into higher numbers of cores. But as I explained, higher numbers of cores are not tremendously useful at the point where we're at, right? Yes, you will see mainstream chips from Intel that have 8 cores and 12 and 16 and 24 and going up, right, over time. But they will not be really terrific deals from an economics perspective or from the perspective of the power that the machine is consuming. Here's a nice pretty picture. This is the KB Lake. Yes, KB is pronounced to rhyme with baby. Just remember that, right? So KB Lake. This is a chip they introduced last year. Just to break this down, what we have here is basically what Intel calls the uncore. This is all the memory controllers and the PCI Express interfaces and so on. We have 4 CPU cores, and then all of this is the GPU. Now, I think this is basically machine colored drawing. I don't think this is actually anything like what the die would look like if you could look at it. But the GPU consists of many small cores that do graphics-related processing. The CPU cores are very much larger. You can see the regular areas. These are caches and register files and things like that. You'll see literally dozens of regular areas within any modern CPU. And they're all just memory, basically. So this is an example of a chip where literally they couldn't think of anything useful to do for a mainstream customer with more CPUs on a chip. This chip is actually a very small manufacturable device. And by the way, if you can see down here, I brought some souvenirs from my time at Microprocessor Report, where every year at our microprocessor forum, we would produce these portfolios that actually are covered with real chips, with the chip specs on them from various vendors that would pay us for the privilege of taking their chips and putting them on these portfolios. Now, we did this for quite a few years. I've only bought 3 of those with me, but I've got a full set. For a while, we were running 2 conferences, and we were producing a ton of these souvenirs. They're pretty cool. This one is a special one because it was from the same 1996 event where we launched this poster. And this portfolio includes a genuine Intel 4004 alongside a Pentium Pro, which was their best CPU at the time, to show physically the progress they had made in the previous 25 years. The 4004s, incidentally, were complete working chips that they had in a warehouse in bare die format. They hadn't been packaged. There was no wires attached to them yet. But they were available in case somebody, showed up somehow with some kind of order for these old chips. They had long since given up on ever selling them again. And so when we said we would like to actually get some, they said, I think we can hook you up. And so we've got like 1,500 genuine 4004 die from Intel, like 25 years after they were made, or at least after they first came out. I don't know how old these actual chips were, but probably 20 years or something like that. But getting back to this, the point here is that Intel couldn't think of good reasons to put more CPU cores on the chip and had to fall back to filling half of the chip, or 40% more or less in this diagram, with graphics. And I can tell you that the commercial value of all of those graphics processors and all the related 3D acceleration features that are in that part of the chip is only like $20, because you could buy a comparable GPU chip to put on the motherboard for less than that, and the difference would basically cover the extra square inch of motherboard space or whatever. So this is by far the least valuable real estate on the CPU here. It's useful, but it doesn't add a lot of value. In the old days, we had a term for this, for 3D accelerators that were not worth very much. It was free D. Free D, right? We're not really getting paid for this. They're buying this part of the chip, and we're giving them this part because we would rather get $5, $10, $20 from a customer to buy our silicon instead of having them buy from Nvidia, for example. Right? Literally, they just put this stuff on the die because it eliminates a market opportunity for a company that could otherwise become a competitor. Now, if you think about multi-core, there are, however, many applications that can use it. They're just not the ones that we tend to run on our PCs. Computer graphics is an example, right? And certainly the biggest one commercially, but there are others. Any kind of signal processing you might be doing, and in fact, some people would argue that many aspects of graphics processing are just a form of signal processing. Many supercomputing applications, like if you're literally modeling atomic bomb simulations, right? Those can be handled pretty effectively on large numbers of CPU cores or other kinds of cores. Various applications in cloud computing and artificial intelligence and network processing and so on are also natural applications for many core designs because they all have the intrinsic opportunity to run many sequences of code in parallel without the dependency problem I was talking about earlier. But almost all of these will work better with something that isn't a CPU than it will with something that is a CPU. And so this gets us into the realm of application-specific processors. The old model of the computer, back in the early days of the PC when dinosaurs like Bill Gates roamed the earth, was that the CPU was all general purpose, right? There was nothing in the hardware of the machine that was unique to a specific application. And every part of the application optimization came from software. But as I talked about the CPU application sensitivity thing, and when you get to things like system-on-chip devices in your smartphones, the vast majority of those chips now is application-specific accelerators for things like video processing, audio processing, and so on. I've got a bunch of stuff about GPUs, but I know I'm running out of time. I've only got 10 minutes, and I've still got some more slides to get through. So I'm mostly going to skip this. This is a block diagram of an Nvidia Volta, their brand new GPU. At this scale, you can't read it, right? So I can zoom in to 1/84th of the previous chip, and that's after disregarding things like the bus interface. You still can't read it. So I'm going to zoom into half of that, and now you can see that, and again, this is 1/168th of the chip, and there are literally dozens of ALUs on this part of the chip, right? These are 64-bit floating point. These are basically 64-bit integers. These are 32-bit floating point. And each of these tensor cores, which is a weird name NVIDIA came up with for reasons I still don't quite understand, is basically a 16-bit floating point ALU. And there are vast numbers of these things on this total chip, right? You can take the number you see here, which is, 64 in each one of these blocks, and multiply that out by that 168 number, and you get an idea of just how much processing power is on the chip. The trick, of course, is keeping it fed, getting data in and out to it. There are things like caches that are on the chip, and that helps, but all of the secret sauce in these chips is figuring out how to route the data around, not so much in how to put large numbers of ALUs on the chip, because people have been doing that for a long time. I don't have a die photo of Volta, but I did find a die plot of Pascal, the previous generation. This is about 17 million transistors instead of the 21 of the previous chip. And you can see that there's almost nothing you can kind of make out except for those large rectangular areas which are caches. In the x86 space, Intel makes these chips called the Xeon Phi series. Basically, these are atom cores that have been augmented by a pair of 512-bit vector processors. And there are 72 of these on this chip. This is a product family that started out as a graphics processor. It was a really terrible idea for graphics processing to try to write 3D accelerator software to run on a large number of x86 cores. I was merely one of a number of people who pointed this out in writing, and then found myself with a job at Intel just a few months later. The first week or so in the cafeteria, I can tell you, was fairly tense, because I had people stopping by to either tell me I was a genius or that I was an idiot and I killed the whole product line before it even launched. And, well, it wasn't me that killed it before it launched, I'll put it that way. In artificial intelligence, we're seeing renewed interest in these very large numbers of cores on a chip. This is a company called Esperanto Technologies, run by an old friend of mine, Dave Ditzel, best known as the founder of Transmeta, although I worked for him when he was a vice president at Intel, the company that he had spent his entire time at Transmeta running down in every interview we ever had. Basically, this is 4,096 complete little 32-bit processors on a single die. This isn't actually a picture of the die. This is just a block diagram. It's really about the simplest one I've ever seen. Plus 16 larger cores. But they intend to aim this at artificial intelligence because that's one of the few workloads where this kind of makes sense. Now, where do we go next? We do still have some generations of process technology improvement to look for, so that will give us probably, I would guess, at least 10 to 12 years of slow, steady progress. Most of the effort is going into other areas of the machine because they provide better return on the investment. But let's talk about the bigger opportunity that I see out there. And to do this, I have to go back and quickly review the history of software on the PC. You go back to the 1950s, you had machines that were programmed by literally plugging wires in or by somebody writing binary machine code on paper by filling in boxes, right? 111000. And then laboriously transferring those into the machine and running it, and very painful stuff, right? No automated software assistance. We then got compilers for assembly language. We went through a few phases of classes of programming languages, like programs that were optimized around the idea of variables, like BASIC, Fortran, etc. More structured approaches to data storage and manipulation. And then finally, object-based languages, which are sort of the big thing today. And I have to tell you a little bit more about the way that we design CPUs. And there's a difference in the CPU design process between the architecture of the CPU and what we call the microarchitecture of the CPU. The architecture is basically what the programmer's official view of the machine is, and the microarchitecture is how the machine was actually designed. And they are not the same. Definitely not the same. The thing that's above architecture, and this is just a term I made up, and since I'm the guy on stage, I get to make up my own words if I want to, is macroarchitecture. And this is sort of the high-level details of how the machine views the rest of the world. For example, all computer processors, essentially all that we have seen over the last 50 years or so, or even longer, have this idea that there are registers in the machine that store data, and there is RAM in the machine that stores data in a different way. And then there is like disk drives and mass storage that store data in yet another way, right? So we have register numbers or register names, because generally you have to treat them as names. There's addressed memory, and there's file structured storage. There's rules about how all of these things work together to build systems. And the fact is, we're still left with a machine model that originated in those days of hand-assembled